We'll study the symmetries of a regular polygon. These symmetries form dihedral groups. So let's start with a square, for instance. And let's list the symmetries of the square, which include the rotations by 90 degrees, by 180 degrees, by 270 degrees, or just the identity. So 4 rotations, the smallest one of which satisfies r to the 4th is equal to 1. And then we have 1, 2, 3, and 4 reflections along axes, and they all satisfy that their square is 1. So for the square, which has 4 sides, we find 8 group elements, and we'll call the group is formed by these rotations and reflections D8. Now, 2 reflections form a rotation. So for instance, if I first do one reflection along one of these axes and then a second reflection along the other axis, they form an angle of 45 degrees. And if I compose them, I get a rotation by 90 degrees, which is already in our group. So the group is complete. You could also think about point reflections, and point reflections in the two-dimensional plane are just rotations by 180 degrees. So we also took care of those. So this is a dihedral group. Of order 8. Dihedral refers to the angle between two faces of a solid. Here, this is not really relevant because we're studying regular polygons in the plane, but that's the etymology. So now what happens for a regular n polygon? Well, that's easy to imagine. We have a rotation r by 360 over n degrees, and it will satisfy r to the n is 1. So we have a cyclic subgroup of order n inside D2n, which moreover is normal. The quotient is Z2. And then we have reflections, of which there are, again, n. And moreover, we can say that if we have rs squared, well, a rotation composed with a reflection is again a reflection, so this is 1. And this also tells us how to commute r and s, because this basically tells us that r is s because s square is -1 as well. S inverse is s because s square is 1. All right, so we have our complete group D2n, also sometimes noted Dn because it refers to the regular n polygon, is equal to the group which is generated by r and s, where r satisfies that r to the n is 1, s satisfies that the square is 1, and then moreover we have that the square of rs is 1. This defines the group entirely. So this is that dihedral group. Of order 2n, which is the symmetry group of a regular n-gon. So this is an example of a Coxeter group, basically because it is generated by reflections. Moreover, we can draw its Cayley graph, indicating the order of various group elements. So for instance, for D8, we would have the identity element, and then we had a cycle of order 4 for the rotations by 90 degrees of the square. And then we have 4 reflections. 2, 3, 4. 8 nodes, 8 group elements. This is the Cayley graph for D8. This is for D4. It would be, we would have a rotation of order 2, and then 2 reflections of order 2, and the little thought shows that this is nothing but the Klein group. Z2 square. And so on. So for instance, D12 would have 1, 2, 3, 4, 5, 6. This, and then another 6 attached. So these are the Cayley graphs. So as mentioned, we have a standard normal subgroup. And also, it is true that if we label the vertices of the regular polygon, we see that the group D2n is automatically a subgroup of Sn, the group of permutations of n elements, because each symmetry corresponds to a permutation of the vertices. And then finally note also that, for instance, D3 is S3. In fact, the dihedral groups appear very often in the classification of small non-abelian groups. This is one of the spots where dihedral groups are handy.